Good day, editors, reviewers, ladies and gentlemen. The title of my paper is Identification of Working Memory Status in Children from EEG Signal Features using Discrete Wavelet Transform. In this presentation, I will first introduce you to the term used in the title and the project itself. Then I will move on to the methodology used in the work and discuss about the results and discussion, and finally I will conclude my presentation. Working memory is a cognitive system that allows the temporary storage and manipulation of information. It is responsible for holding on to, organizing, and manipulating information to complete a task. A working memory has a limited capacity. It can hold a small amount of information for a short period of time. Therefore, the working memory has to be trained to focus on relevant details and ignore irrelevant ones. It is important to diagnose working memory issues in children at an early stage. It's because we can use the diagnosis to identify and correct learning issues related to it. The working memory has three important components. The first is the central executive. Second, phonological loop. Third, visual spatial sketchpad. The central executive oversees all activities of working memory as well as tasks like planning, problem solving, decision making, and others. The phonological loop stores verbal information such as sounds or words using sub-vocal rehearsal. The visual spatial stores visual and spatial information such as shapes or directions. According to the new working memory model, there is another component which is called episodic buffer. It merges information from the loop, sketchpad, and long-term memory and perception into a clear episode. Electrocardiogram, or in short we call EEG, is a non-invasive technique used to measure electrical activity in the brain through electrodes attached to the scalp. EEG has been used in several studies, for example, in the detection of brain injury, monitoring of post-stroke rehabilitation, diagnosing neurological disorders, and others. The conventional method of evaluating working memory performance is called the hands-on test method. This method uses a set of multiple questions. This method is time-consuming since recording scores for a large sample size requires a significant amount of effort and may not yield accurate results. That is why we have to explore a better technique to evaluate working memory performance. Some researchers have utilized EEG to identify working memory impairments in children using wavelet analysis, but they do not look at the relationship between the EEG features and the working memory states. The objective of this work were to identify the relationship between the game score and the EEG features of children and adults when performing working memory related tasks, and to determine the working memory status of the subjects from EEG features. This is the process of extracting features from EEG signals with working memory status information. It includes EEG acquisition, EEG signal processing, EEG analysis, and finally, feature extraction. During the EEG recording, the subject has to play two games, which are called dot game and the shape game. They have to remember the dots and shapes in the correct order within the grid box. The sample of dot task, you can see it's here, and the sample of shape task is here. The shape game is the same as the dot game, except that it will display the shape on the screen. And it has an interstimulus question which is displayed after it displays the shape on the screen. The purpose of the inter-stimulus question is to check whether the subject can remember the correct shape or not. The game has 9 levels. The number of levels is equal to the number of dot sequences that the subject needs to remember. In the EEG signal acquisition and processing, 5 adults aged 23 to 24 years old and 5 children aged 8 to 12 years old took part in the data collection. We use 5 electrodes to record the EEG signals. They are located at FP1, FP2, F3, FZ, F3, and finally F7. These electrode positions are associated with the working memory. We then remove the baseline drift using high-pass Butterworth filter with a cut-off frequency of 0.6 Hz and a sampling frequency of 500 Hz. We perform signal analysis using fast Fourier transform and power spectral density. Before we perform the signal analysis, the signals were band-pass filtered using several band-pass filters. This is to check the frequency content of the signals and also the power of the signals. In the feature extraction, we perform a discrete wavelet transform using Debuchy order of 4 to separate the signals into multiple scales. Figure 5 shows the subband of decomposition level with a frequency range. We took the beta band signal, which is in the range of 15 to 30 Hz, alpha band signal 8 to 15 Hz, theta band signal 4 to 8 Hz, and delta band signal 0 to 4 Hz to calculate the F ratio using the equation 1. We also calculated band power using equation 2 and the ratio theta over beta power. We have discovered that the minimum and maximum F values of children's EEG are smaller than those of adults' EEG. The beta power range of children's EEG is higher than that of adults. The children have greater theta over beta power compared to adults. Another important or interesting finding is that when the F value decreases from task 1, which is dot game, to task 2, which is T-shaped game, the beta band power and theta over beta increase and vice versa. Table 1 shows relationship between features, game score, and memory states. We have identified 5 memory states, which are distraction, daydreaming, confusion, losing focus, and active state. Distraction is demonstrated from the decrement of game score and beta band power, and the increment of F value and theta over beta power. For daydreaming, we can observe it when the game score, F value, and beta band power decrease and theta band power increase. For the confusion state, all the parameter decrease, which are game score, F value, beta band power, and theta over beta power. For the losing focus, we can observe it when 2 parameters, which are game score and F value decrease, and beta band power and theta over beta power increase. For the active states, it is demonstrated from the increment of 3 values, game score, F value, beta, and beta band power, and the decrement of theta over beta power. As I mentioned previously, the work focused on the feature extraction of EEG signals from children and adults using discrete wavelet transform and the identification of the memory states based on the extracted features. We have extracted 3 features from the EEG signals using discrete wavelet transform. They are F value, beta band power, and theta over beta. And we have identified 5 memory states, which are distraction, daydreaming, confusion, losing focus, and active state. From the analysis, we have established the relationship between the features, game score, and the memory states. The result demonstrated that the DWT, or discrete wavelet transform, could be used to determine the memory states through the extracted features. This work provides an efficient method of assessing the working memory status of the children and adults from EEG signals. We would like to thank the Ministry of Higher Education Malaysia and the Research Management Centre, University Technology Maram Malaysia, for their financial support, as well as the Microwave Research Institute in the School of Electrical Engineering, College of Electrical Engineering, University Technology Maram Malaysia, for their support and provision of facilities. With that, thank you very much for your attention.